Ladies and gentlemen, today I will talk about a critical issue in aviation, the challenge posed by a complete engine failure. This situation presents pilots with significant obstacles that must be addressed under immense time constraints and psychological pressure. Specifically, two key problems arise that require immediate attention. First, the pilot must identify a suitable landing site. If no official airport is within reach, an appropriate emergency landing area must be selected. Second, the glide trajectory to that site must be calculated with precision, as it differs greatly from an approach with engine assistance. In a normal flight with functioning engines, energy can be supplied at any time. However, in a glide, only the available potential and kinetic energy of the aircraft, both of which are continuously decreasing, can be used. This is why accurately modeling the aircraft's energy balance becomes crucial. The glide trajectory needs to end exactly at the runway threshold with the correct altitude and heading. Excess energy can be dissipated through specific flight maneuvers, such as turning or by using flaps. But crucially, misjudgments in external conditions like wind or thermals cannot be corrected by simply increasing thrust. Unfortunately, the commercial landing assistance systems currently available, such as Garmin, ForeFlight, or SkyDemon, offer only limited solutions to these issues. Some systems, like Garmin Autoland, still rely on engine power, while others, like Garmin Smart Glide or SkyDemon, only display the area that can be reached in a glide. However, they do not provide an exact calculation of the glide trajectory, which makes these systems unsuitable for fully autonomous applications. Furthermore, no known system offers data on emergency landing sites outside of registered airports, which is crucial when the aircraft's altitude is too low for an extended glide. This is where the Safe-to-Land system developed by our team comes into play. Safe-to-Land addresses both of these problems. By using advanced pattern recognition techniques based on artificial neural networks, we are able to identify suitable emergency landing sites from geodata, such as digital orthophotos, digital surface models, and OpenStreetMap. For instance, in North Rhine-Westphalia alone, over 103,000 potential emergency landing sites have been identified and stored in an emergency landing site database. Moreover, Safe-to-Land uses our concept of kinematic chains to create glide trajectories. These trajectories model environmental changes along the flight path, such as air density and wind vectors at different altitudes, both efficiently and precisely. The system generates control instructions in the form of target heading and target bank, which are displayed to the pilot via flight director. Additionally, we've demonstrated that the system is capable of fully autonomous landings by converting these control instructions into autopilot inputs. This has been successfully tested in a flight simulator. During this presentation, we will demonstrate the Safe-to-Land system through a workbench connected to a flight simulator. This setup allows for quick evaluations of the trajectory algorithms. The parameters used to model the glide characteristics, such as optimal glide speed, glide ratio, wind direction, and wind strength at different altitudes, can only be estimated roughly, and they may change during the approach. Additionally, there are interactions to consider. For example, an overestimated glide ratio will affect the aircraft's performance in a way that is similar to encountering unexpected updrafts with the correct glide ratio. With the workbench, we can explore how such disturbances can be compensated for by dynamically adjusting the trajectory. For instance, deploying the flaps earlier during the final approach can mitigate the effects of updrafts. In cases where these disturbances become too severe, recalculating the trajectory might be necessary. We can identify this need by observing the predicted touchdown point relative to the emergency runway threshold, as determined by the kinematic chains. If the predicted touchdown point is too far beyond the threshold, the flaps will be deployed earlier. Conversely, if the predicted touchdown point no longer falls on the runway, flap deployment will be delayed or even omitted altogether. In summary, the FLUVE Safe-to-Land system offers reliable support for pilots facing an engine failure scenario. It not only guides them to a safe landing, but is also capable of performing the emergency landing autonomously through the autopilot system. Thank you.